So I have here the setup for a type of differential equation that is called a mixing problem. And mixing problems are called mixing problems because they usually involve some sort of a fluid with something in it that's dissolved or getting mixed. So right here you see I have this shape. This is a pool. So imagine there is some water in this pool. There's some water, and there are two things happening to the water. Three things, really, if you count it. So, first, there's some salt in this water. So, little crystals of salt, and you can assume that the salt is all dissolved fairly evenly in it. Well, for the purpose of the problem, it'll be dissolved exactly evenly. Now, the second thing is that there is a leak here. So, the amount of water in this pool is not constant. There's a leak that is carrying out a certain amount of the water, and with that water it's carrying out, there is also a certain quantity of salt that is getting carried out. Now, the second thing is that you have a hose here, and the hose is bringing in a certain quantity of new water. So you have some new water here, and it's coming in. And as before, there's salt in the hose's water. So, you have salt going out, salt coming in. Thing is, the salt that's coming in is coming in at a variable rate. So we can say the amount of salt coming in at any time t, s of t, is some quantity, maybe the cosine of t plus 1. And this means that for every gallon of water that's coming in through the hose, there's going to be this much salt. So, let's define some actual conditions here to make this problem concrete. So, let's say the pool has a capacity to hold 800 gallons of water, and it starts with 400 gallons. So it's starting half full. But so we can say maybe 10 gallons per minute, this is this hose up here, are coming in. 5 gallons per minute are leaving through this pool's leak here. So 5 gallons per minute are leaking out, and that accounts for this. Now we just have to say, so we know that the leaking out water is going to be leaking salt at the same amount that is up. We're going to be assuming it's mixing perfectly evenly at every instant of time. So however much salt is dissolved in the pool, it's going to be leaking out. We know we have the variable amount of salt coming in through the hose. We can say maybe we start with 20 pounds salt dissolved at the beginning. So at time equals 0. So at t equals 0. And with this, we can begin to think about how we would solve this. Let's just also define one more thing, which is that we're going to have a variable q of t. This is going to be our function that's going to define, this is salt at time t. So this is the ultimate function we're going to be trying to be solving for. But it's going to be a long journey because this is quite an intertwined problem. Not only do you have salt leaving at a rate that is dependent on how much salt is in the pool, that's the leak. You also have salt coming in, that's dependent on what the time actually is. So this is an intricate problem here, but we can write it fairly easily as a differential equation. So how could we write this as a differential equation? Well, it's fairly makes sense that we would be writing this as some kind of change in Q. So Q prime of t, this is the change in the amount of salt at any time t. Well, what is this going to be? Well, we know we have two ways the salt is changing. We have the amount of salt that is leaving. We have this salt, and the amount of salt that's coming into the pool. That's that salt. So if we make use of that, we can first talk about the hose here. So 10 gallons per minute coming in. So we can write however much salt is coming in here. We're going to multiply that by 10 because there are 10 gallons of it. And then, well, how much salt is coming in? We know we have S of t here. So that's 10 times S of t, or 10 times the cosine of t plus 1. That is how much salt is coming in all the time. And now we have to account for the salt that's leaving. So we can subtract 5, which is 5 gallons leaving per minute, 5 times however much we're going to do here. And this is a little bit harder to think about because here we have a variable amount of salt leaving. But it is also completely dependent on how much salt there is because we're thinking 5 gallons leaving per minute. Well, how much salt is in each gallon? Well, if we assume it's perfectly mixed, the salt per gallon should be Q of t, which is the total salt. This is total salt. And we should be dividing it by, well, the amount of volume of water there is. This is the volume, right? If we say salt divided by volume, we're going to get salt per unit volume. But what is this volume? Well, you could say that V of t is, well, V of 0 is starting at 400 gallons, right? So, and at all times there's 10 gallons coming in, and there are 5 gallons leaving. So that means there's a net of 5 gallons. So we can write that V of t, this is the volume of the pool at any time t, this is going to equal, well, at time equals t, you have 400 gallons. And at every time period, you're going to have 10 gallons coming in and 5 gallons leaving. So we add 10 gallons, we subtract 5 gallons. That is the same thing as 400 plus 5t. Which is to say, every time step, you're going to have 5 gallons coming in. Now, we can write this as Q of t, if we go back to our differential equation here, minus 5 times Q of t divided by V of t, which we know is 400 plus 5t. Now that we have this, we're actually done writing our differential equation. This is what we're going to be working to solve. So let's get solving it. I'm going to copy and paste it down a little bit lower so that I have it when I scroll down. And now that we have this, the only real thing to do is to solve. So, how would we solve this? Well, one thing you might notice about this is that it is in the same form as something called a linear differential equation. Linear first order differential equation, because the highest order derivative we have is 1 over here. So, the general form for the linear first order differential equation is when you have some function f of x times y, which is your function, plus some other function, which I should call g of x, times the derivative of y, equaling some third function, h of x. And you can see we can turn our differential equation into this. So let's get a new color and do some quick rearranging here. If we add this 5 times q of t divided by 400 plus 5t, we'll have ourselves in this form. So let's do that. Let's add it. So we're going to get 5 times q of t divided by 400 plus 5t plus q prime of t. This is all equaling 10 times the cosine of t plus 1. So now we have our differential equation in this form. And what's special about this form is that there's a magic function that we can multiply in to both sides, because this does look awfully close to what we might call the derivative of a product of functions. After all, it doesn't look exactly like it, But you have a q of t here, and you have a q prime of t, and we'll remember, if you have the derivative of two functions, so just to say, if you have the derivative with respect to time of a function f of t times a function g of t, just recall this equals f prime of t times g of t plus regular f of t times g prime of t. So if you imagine g of t being q of t, it's not quite there yet, but it's pretty close to this being f prime of t times q of t plus the regular function times g of t, if we found a magic function that we could multiply in. And if we quickly rewrite our function here, we see we have this constant here, 5 divided by 400 plus 5t. We're multiplying that into q of t. So if we were to multiply something in, it seems feasible that we could turn it into this form here in magenta, this product. And once we had that, it would be fairly easy to take the integral of this, because if you take the integral of the product, it'll just turn back into the product, and then you'll have the integral of the right side times the other function, and it'll be pretty simple, because then you can just divide by f of t. So, sorry if I'm going way too far ahead here, but let's just write out what I'm thinking, and in the correct color also would be nice. So this equals 10 times the cosine of t plus 1, and at this point, what we're trying to do is we're trying to think of a function. I'll call it mu of x. So we're trying to think of a mu of x that if we multiplied it into the left side of this equation and into the right side, it would turn the left side here into a product rule derivative. So what could that function be? Well, we should leverage here that we have this term with the 5 divided by 400 plus 5t. This is going to be useful because it makes it different from this term. So when we multiply a function in, we're going to be to get the derivative on the q of t and then the regular function on the q prime of t. So at the risk of being too abstract here, let me propose a function, mu of x, that might work, and let's see if it does. So what I propose we should do is we should have multiply into each side e to the integral of 5 divided by 400 plus 5t dt. Why might this work? Well, when we multiply it into the first term, we're going to have 5 divided by 400 plus 5t times e to the integral of 5 divided by 400 plus 5t dt times q of t. And if you imagine that this was actually the product rule, and then this would be the derivative of this function, because when you take the derivative, the e to the x part stays the same, but then the chain rule, you take down the integral. So again, very abstract here. Let's just actually multiply it in. So if we multiply in mu of x to both sides, then we get e to the integral of 5 divided by 400 plus 5t dt. And this is also being multiplied by 5 divided by 400 plus 5t out here. And then this is multiplied by q of t. And then we add here, just multiplying it in still for each term, 5 e to the integral of 5 divided by 400 plus 5t dt times q prime of t. And then this equals e to the integral of 5 divided by 400 plus 5t dt times, and we're going to have to go on to the next line here, 10 times the cosine of t plus 1. So, now that we have this here, look at how similar this looks to a product rule. Here we have this function here, and if you're imagining it, g of t is q of t, so for this first term we are not taking the derivative of q of t. So this second function here, we have to be taking the derivative of it. So if you imagine that that function is See, here we're taking the derivative of q of t, g prime of t. So the actual function, f of t, is going to be this integral function. So if you imagine this here, these two things being multiplied together, this is the derivative of f of t, and indeed, it does look like if we took the derivative of e to the integral of 5 divided by 400 plus 5t dt, the integral would come down with a chain rule as the derivative, which is this. And to make it a little bit clearer, we can rewrite this by actually evaluating what mu is. And if we evaluate mu of x, we get this equals e to this. Now, how would we evaluate this actual integral? Well, we can use a simple u substitution because we have a 5t here and a 5 here. So we can say, so let's do it in a good color. So let u equal 400 plus 5t du is the derivative is 5 dt. So dt, which is the term we're going to be substituting here, du divided by 5. So when we take this here, we can substitute in u. So we have 5 divided by, well, 400 plus 5t, that's u. dt, we substitute in for du divided by 5. Oh, hey, 5's cancel out, so you're left with e to the integral of du divided by u. And just want to make it clear these are different equations here. So if we do some weird formatting and we actually jump this over to here now, we get that mu of x, this is going to be, or rather it's mu of t. Sorry if I've been writing that incorrectly here. Mu of t is going to be e to this integral. But this integral here, du divided by u, that's the same as just 1 divided by u du. So we know that's the natural log of the absolute value of u. And if we plug that in, we're going to get this equals e to the natural log of 400 plus 5t. And quickly we will notice we don't actually need the absolute value here because, well, t is always positive. Multiplying by 5 doesn't change that. Adding 400 doesn't change that. So this is always going to be a positive value. So this equals e to the natural log, regular parentheses, 400 plus 5t. And of course, e to the natural log of something is just that thing. So we have 400 plus 5t. So now that we have this, we can multiply this in, and we can substitute it in for this e thing. So what do we notice when we do that? Well, let's rewrite this. So we have 5 divided by 400 plus 5t times e to this, but we know that e to that, which is this mu function, that is just 400 plus 5t. So 400 plus 5t. Now, if we multiply this by q of t and go over to here, we see we have same thing, so plus 400 plus 5t times q prime of t. And again, now here we have the same thing again, so 400 plus 5t times, now 10 times the cosine of t plus 1. Whew, long equation. But as we see now, this 400 plus 5t, it cancels out. So now, all that we're left with is this 5 times q of t plus 400 plus 5t times q prime of t equals 400 plus 5t times 10 cosine of t plus 1. Whew. Again, long equation, but it's only getting smaller at this point, which is a good sign. And if you look at this, this is exactly what we were looking for with the product rule. Here we have q of t times some, hopefully, derivative of some function. And of course we know if this is actually the product rule, when we're multiplying by q prime of t, that means that this function right here would have to be the other function, so 400 plus 5t. And indeed, it certainly looks like the derivative of 400 plus 5t is 5. So we did it correctly. And what that means is that we can simplify this down. We can rewrite it as a nice green color. The derivative with respect to t of q of t times, so this 400 plus 5t times q of t. And this equals 400 plus 5t, and I'm going to move the 10 over to here. 10 times 400 plus 5t times the cosine of t plus 1. And with this, we're running really long on time, so we're going to actually solve this in the next video. See you then.